Hello and welcome back. Today we're going to review Unit 11, the circular functions, which are the trig functions. We're going to break this unit into review into two different videos. The first video we're going to focus on things about angles and trig functions in general, evaluating them, find the reciprocal functions, and so forth. In the second video we're going to get into the graphs of the functions and how to approach some sinusoidal modeling problems. Here is a brief overview of the lessons that we learned. Just take a moment to look at that. And also, here are the common core standards associated with the trig functions. So take a moment, pause the video, and get a sense for these standards before moving on. So let's get right to it. There are some formulas that we had in the trig unit that you'll have to know. And the first one isn't really a formula, but it tells you how to define your sine, cosine, and tangent values of an angle based upon the sides of a right triangle. So whenever you have a right triangle, you can find the sine of the angle, acute angle, the cosine of an acute angle, and the tangent of an acute angle. Now these are all based upon one of the acute angles, and you can label the sides of a right triangle in respect to that acute angle. The hypotenuse is always across from the right angle. The opposite is always across from the acute angle, and the adjacent is always the leg that is next to the acute angle. So make sure you label your diagrams appropriately if you're dealing with a right triangle situation. The sine is opposite over hypotenuse. That's why it's O and H. And cosine is adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. I like to write it like this. So, ka, toa, because that kind of more clearly shows the relationship between the sides. But either way, as long as you know that phrase, so, ka, toa, you can find out the sine, cosine, and tangent of any angle. Another formula that we saw was the Pythagorean identity. And that relates to the Pythagorean theorem because it looks very much like it. So if you have sine of some angle squared, and you add it to the cosine of some angle, square that, you get 1. 1 squared. A squared plus b squared equals c squared. That's why it's called the Pythagorean identity. Now you might see it written as sine squared of x plus cosine squared of x equals 1. Okay? It's just a notation thing. Okay? You might see it written that way. Sine squared of x is really just the same thing as saying this function sine x squared. Those are the exact same thing. And the last formula was arc length formula. S equals r theta. Okay. S stands for the arc length. R is the radius, and theta must be in radians. Because if you remember, the definition of radian is how many radii you are around a circle. So here's a radius. 1 radian is 1 radius around the circle. Now it doesn't matter how big or small your circle is, it's the same proportion of the circle around from the positive x-axis or wherever. Okay, so the arc length is just going to be however many radians you are around the circle. Okay, so that angle must be in radians. Right, now, we dealt a lot with angles in the trig functions, and in the past you've only dealt with sine, cosine, tangent of positive acute angles. But as you saw in this unit, we had negative angles, we had obtuse angles, you had right angles, linear angles, and so forth. Okay, any angle that you can put into a trig function will work. So, there's some terminology that you should be really familiar with. Standard position is always formed from the positive x-axis counterclockwise to the terminal ray. So in the diagram here, which was provided to us in our notes, here's the positive x-axis. That's that ray we're going to be starting from. It's also called the initial ray. The terminal ray in this diagram is right here. Okay. What that's telling you is that this is the angle right here that's in standard position. Okay. It could be in any quadrant. It could be 90 degrees. If it's 90 degrees, then the terminal ray would be here on the positive y-axis. If it's 180 degrees, then the terminal ray would be the rest of the x-axis, okay, and so forth. You can have it anywhere in there. But the standard position for an angle is always going to be between 0 and 360. Okay. Any angle between there has a standard position. Now, you can also have positive and negative rotations, positive and negative degrees. Okay. Positive is going counterclockwise, and negative, the angles go clockwise. So the sign in front of an angle just indicates which direction you're going. So positive direction would be this way, negative direction would be going that way. Now you also have the term coterminal angles, and those are just angles that share the same terminal ray. Now there are 360 degrees all the way around a circle, so it takes a 360 degree rotation to get back to the terminal ray. So whatever your angle is, you can add or subtract 360 degrees or some multiple. Okay, so some multiple, so n is some integer, 1, 2, 3, 4. You can add 720 and so forth. You can subtract 720, you can subtract 360, any multiple of 360, adding or subtracted from an angle. So for instance, if I have the angle is 20 degrees, a coterminal angle with it would be adding 360, which is 380 degrees. Okay. I could also subtract 360 to give me negative 340 degrees. Okay, and I can keep going. Negative 700 degrees. Okay. There's an infinite number of coterminal angles for any angle in the diagram. So if you're given a 380 degree angle, what I would suggest to do is always find the angle that's coterminal between 0 and 360 to help solve the problem. Now reference angle is what we're really using when we're evaluating trig functions in the long run, no matter where it is in the quadrants on your axes. So the reference angle is always the positive angle formed with the x-axis. And reference angles will always be between 0 and 90 degrees. Graphically, okay, what you're just going to do is wherever your terminal ray exists, you're going to draw a perpendicular to your x-axis. And that angle that's formed with the x-axis is your reference angle. Okay, but there's some general rules to follow if you want to approach this more formulaically. If you're in quadrant 1, well, you have the reference angle. It's going to be whatever angle you have. If you're in quadrant 2, what you're going to do is you're going to take 180 and subtract off the reference angle. Because in quadrant 2, this is 180, but you don't want the angle in standard position. You want just to have the positive acute angle that is formed with the x-axis. And then if you're in quadrant 3, then you do the angle minus 180 degrees because you'd be larger than 180 degrees at that point. And quadrant 4, you do 360 degrees minus the angle. Alright, pause the video, make sense of this, and write down anything you need to before moving on. Another big thing you're going to be asked to do is to convert between degrees and radians. It's important to note that pi radians is equivalent to 180 degrees. That's what you're going to use when you're doing conversions. So if you're given from degrees to radians, I want to cancel out my degrees, so I'm going to multiply it by pi over 180. That will cancel degrees and leave me with just radians. Okay, and if you multiply that out, you get approximately 1.36 radians. Okay, now you can leave your answer as 1.36 radians, or you can leave it as 1.36. What tells you that it's radians or versus degrees is whether or not you have the degree symbol or if you have the word degree. Okay. So there's no degree symbol here, so 1.36 is fine. And that's a decimal approximation. It's actually 1.361356817. Okay. Converting from radians to degrees, I want to cancel radians, so I'm going to multiply by 180 degrees over pi radians. Okay, and when you do that out, you'll get something like 249.24 degrees. Okay, and depending on the problem, it should say how to round your values. 249.24 degrees. And this last one, we have degrees, so we want to convert to radians. So I'm going to multiply by pi over 180. Now typically in these types of problems, the pi's will end up canceling. In this case, they end up becoming squared. 10 pi squared over 180, that gives you approximately 0.548 radians. Another thing you're going to be asked to do is to find the arc length that's formed from a specific rotation. As was mentioned in the formulas page, that the arc length formula is S equals R times theta. But we noted that the theta must be in radian mode. So we have to convert that 225 degrees into radians at some point. So if I want to find the arc length formed from a 225 degree angle rotation with a radius of 6 feet, then I'm going to take the 6 feet, multiply it by 225, but I have to convert that into radians, so I'm going to multiply it again by pi over 180. You can convert that to radians first, but then you're going to get a rounded answer, so just got to be careful about your rounding. I like to put it all in one shot. So this is your theta in radians. Okay. Multiply that out, you get 23.5619449. So approximately 23.6 feet. Okay, that's the length of an arc formed from a 225 degree rotation with a radius of 6 feet. So here is an example. So here's 6 feet. 225 will bring me to about maybe here. So this length right here is 23.6 feet. Make that a little better. 23.6 feet. Okay, that arc with a radius of 6. Now, you are going to be expected to possibly construct the unit circle. Okay, and what that means is for each of the angle measures multiples of 30 or 45 degrees, to find the coordinates of the points that lie on the unit circle. Now you could be dealing with given degrees, or you can be given in radians. So on the circle here we have the degree measure, we also have the radian measure, and we have the points. All of these are formed through special right triangles. The 30, 60, 90 right triangle, and the 45, 45, 90 triangle, which happens to also be an isosceles triangle. Okay. Now, in the size of a right triangle, we're going to be dealing with a hypotenuse of 1, because if you look at the unit circle, say you were asked to construct this unit circle, your hypotenuse that is formed, because it's a unit circle, will always be 1. Now, across from the 30 degree angle is going to be the 1/2, half of your hypotenuse. Across from the 60 degree angle is root 3 over 2. You can use the Pythagorean theorem to recall that and how to get those. The 1/2 comes from the fact of splitting an equilateral triangle in half. Okay, so imagine you had the rest of an equilateral triangle here, split it in half, so therefore this side has to be 1/2. and then use Pythagorean theorem to find out the length of the third side. But you should have that special right triangle memorized. So for a 30-degree triangle, you can put that in the diagram to help figure out the coordinates of this point right here. And here would be the 1/2, here would be the √3/2. Just going to get to something we're going to see in a moment, which is the y coordinate of your point is your y distance, and your x coordinate is your x distance. Okay, and you're going to see in a moment how that relates to sine and cosine. So let me erase that off of here and look at the special right triangle 45, 45, 90. Now you can set x and x both sides because they're both 45. It's an isosceles triangle. Either way, you're going to get √2/2, √2/2. So if you were to try to figure out the coordinates of the point, this is the 45-degree angle because this is the 45-degree location. You would have √2 here over 2, √2/2 here, and this is your x coordinate, this is your y coordinate. Okay. And you can just repeat that all the way around the circle if you're asked to create the unit circle. So for instance, for 150 degrees, what you want to do is you find the reference angle. The reference angle ends up being 30. So you're going to put 1/2 here, √3/2 here. But I'm going the negative direction, so my x coordinate is going to have a negative √3/2. And my y is going the positive y direction, so it's going to be positive 1/2. Okay. And you can put that special right triangle anywhere on this unit circle to any of the multiples of 30, so 30, 60, 90, 120, 150, 180, and so forth, okay? And any of the multiples of 45, so 45, 90, 135, 180, and so forth. Alright, so that's how you construct the unit circle. Notice there's some special points that are unique, so 0 degrees is going to be 1, 0. 90 degrees is 0, 1. 180 is -1, 0. And 270 was kind of cut off there, wasn't it? So 270 degrees is down here, and you have 3 pi over 2 radians. Alright, pause the video, write down anything you need to before moving on. Now let's get into the Pythagorean identity. You could actually use the Pythagorean identity, which is the sine squared theta plus cosine squared theta equals 1. Now in the formula page I use x, but that could just represent any angle. This is the Pythagorean identity. You might see cosine come first. Cosine squared plus sine squared, same thing. Okay. Now you can use this to help find out the value of another trig function. For instance, if you know the cosine of x is 0.8, notice you can plug 0.8 into cosine and then you be able to solve for sine. So just practice this. So sine squared, and here's where I'm going to write it in the other form, sine theta squared plus cosine theta squared, because it might be easier to work with it in this problem. I'm going to substitute 0.8 in for cosine. That gives me sine theta squared plus 0.8 squared is equal to 1. Okay. Working through this problem, I get 0.64 is 0.8 squared. Subtract that from 1. And I get 0.36. So sine theta, and don't forget about this, when you take the square root of both sides, you have to remember the square root principle. It becomes plus or minus the square root of 0.36. So sine theta is plus or minus 0.6. Okay, you can use the Pythagorean identity to find the value of a sine. Now, to find out which one it is, you'd have to know some more information, because cosine could be in quadrant 1 or quadrant 4. Notice that we have two different locations. Okay. It actually gets into something we're going to look at in the next slide. Okay. Now you could also do this algebraically as well. I mean, you could set up a right triangle. Say I'm dealing with angle x, so I'm going to put x here. Cosine is adjacent over hypotenuse, so I can put this over 1.8, and then I can solve for that length using the Pythagorean theorem, which sine is your y value. Okay. But you might be asked to specifically use the Pythagorean identity to solve for a particular trig function. Okay, which gives us what we were kind of just talking about. On the unit circle, the sine is going to be the y coordinate, because it's really y over the radius, okay, and the radius is going to be 1. Okay. Cosine is going to be the x coordinate, okay, because in the unit circle it's x over 1, but in any circle it's x over the radius. Okay. I think it's really important to note that sine is really the y and the coordinates at the end of the terminal ray, and cosine is the x coordinate of the terminal ray, what points on there. Okay. Tangent is sine over cosine. Okay. Since sine is the y coordinate and cosine is the x coordinate, it's going to be equivalent to the y coordinate over the x coordinate. So if you're given a point that lies in the unit circle, hence the key point, it lies in the unit circle, otherwise you have to find the radius to help figure out what the sine and cosine are going to be. It lies in the unit circle. The sine is just going to be your y value, negative 0.56. Done. Cosine of that angle is going to be 0.83. Done. And the tangent is going to be the y over the x, so it's going to be negative 0.56 over 0.83, which when you calculate that out gives you approximately negative 0.67469 ... So let's just say negative 0.67. Alright, pause the video now and write down anything you need to before moving on. Which leads us to the reciprocal functions. Okay. Cosecant is defined as the reciprocal of sine. Secant is defined as the reciprocal of 1 over cosine. So it's the reciprocal of cosine. And tangent, that should have been, cotangent. Let me change that. Cotangent is the reciprocal of tangent, so it's 1 over tangent. So in terms of sides, since sine is opposite over hypotenuse, it's going to be hypotenuse over opposite. In terms of cosines, cosine is adjacent over hypotenuse, so secant is going to be hypotenuse over adjacent. It's reciprocals. And tangent is opposite over adjacent, so cotangent is adjacent over opposite. So you might be asked to find another trig function based upon one trig function. Okay. To find all the other trig functions, you have to know two pieces of information. Number one, you need to know the original function you're based upon, and you have to know maybe the sign of another trig function. That will help figure out which particular quadrant you're in. If you're looking at the unit circle, a good way to remember this is an acronym: All Students Take Calc. Some people look at this and say, well, this is the CAST. Okay, but what this is saying is that which functions are positive and in which quadrant. In quadrant 1, all of them are positive. In quadrant 2, only the sine is positive. In quadrant 3, only the tangent is positive. And in quadrant 4, only the cosine is positive. Okay, so it's a good little method to help remember. But, you know, if you think about the x and the y coordinates, that should also help you as well. Okay. So if you're looking at the trig function, tangent. Notice that we're given tangent is equal to negative 12 over 5. Tangent is less than 0, or negative, in quadrants 2 and in quadrant 4. Because in order for that to be negative, you have to have either sine or cosine. One of them has to be positive, one has to be negative. Because it's sine over cosine. Cosine, we're told, is less than 0, and that occurs in quadrants 2 and in quadrant 3. And now looking at these two results, we see that there's an overlap of quadrant 2 in both of them. So that means we must be in quadrant 2. So what I'm going to do is I'm going to draw a set of axes, and I'm going to draw a terminal ray in quadrant 2, and I'm going to draw the right triangle formed with the x-axis. When you're evaluating tangent to the angle, you're dealing with the reference angles. So here is essentially where the reference angle is going to be for that particular angle that we're looking at. Tangent is opposite over adjacent. So I'm going to put the 12 as the opposite and the adjacent as 5, because it's equal to negative 12 over 5. Okay? Now we have to figure out where is the negative going to go. Because it's in quadrant 2, that means the x-coordinate must be negative and the y-coordinate is going to be positive. So we're essentially having a negative 5 there and a positive 12. But you have to find out what this hypotenuse is going to be. I'm going to put a C there. We have to find out what that hypotenuse is going to be. We can use the Pythagorean theorem to do that. If I do negative 5 squared plus 12 squared is equal to C squared, okay, you'll get that C squared is 169. And this is nice because 169 is a perfect square, and you might have recognized that this is a special right triangle, the 5, 12, 13 right triangles. Okay. If you see any special right triangle, feel free to go ahead and put the other side on there. Just make sure that you have the longest side as a hypotenuse. Other right triangles, there were common ones were 3, 4, 5, 8, 15, 17, and 7, 24, 25. Those are our special right triangles. Alright, so now we have the hypotenuse, which means we have the adjacent, the opposite, and the hypotenuse. We can now find out the other 5 trig functions, mainly what is sine, what is cosine, what is cosecant, what is secant, and what is cotangent. Okay. We already know tangent is negative 12 over 5, so we're just finding the other 5 trig functions. Sine is opposite over adjacent. Notice it's in the second quadrant, so it's positive, so it's going to be positive 12 over 13. Cosine is the adjacent over hypotenuse, so therefore it's going to be negative 5 over 13. It's negative 5 over 13 because it's in the second quadrant. Cosine is negative there. Cosecant is a reciprocal of sine, so since sine is 12 over 13, the cosecant is going to be 13 over 12. Secant is the reciprocal of cosine, so since cosine is negative 5 over 13, it's going to be negative 13 over 5. Now, typically the negative goes on the top, okay, so that's why it's negative 13 over 5. And cotangent is a reciprocal of tangent, so it's going to be negative 5 over 12. Here we have the 5 trig functions. Right, pause the video, write down anything you need to before moving on. Okay, and what happened to the slide? Where'd it go? Okay, here we go. And this is the end of this video, so thank you for watching. In the next video, we will go over the graphs of the trig functions and look at some sinusoidal modeling. Thank you for watching, and I'll see you in the next review video.